The idea is to present some problems that I'm dealing with since, let's say, maybe the past 10 years. And so, yes, with some recent attainment that I hope you'll find interesting. Well, okay, so let me say something about the motivation and why this optimally my design problems. The motivation essentially came from some application, and essentially these problems can be seen as a way of understand evolution, even in damage, or to understand how composite materials, let's say, adjust in order to find good equilibrium configuration, and also to, I mean, another let's say aim is the one of modeling Ogden materials, or understand the behavior of fracture and polycrystals, and I mean many possibilities, I guess, are opened by this type of modeling. Let's say that from the mathematical point of view, the main contribution in the sense of modeling, the first contribution has been given by some famous paper by Cohn and Strang. Actually, there are 3 papers, and by Murat and Tartar in the context of electrical conduction. And the models that they propose, both of the creators, are essentially models that don't take into account any type of penalization between the interface, between either 2 phases of the material, or if you think about fracture or damage, between, let's say, zones that are damaged from zones that are not. And then there are many others models in this direction have been developed in these years, and some of them are related to linear elasticity context, and especially in order to detect the behavior of thin structures. And among them, I would like to recall those one by Bouchité, Fragala, and Sapesher, and also in the context of nonlinear elasticity, there are some models obtained by Brides and Fonseca and Frankfurt. And essentially, there are several types of approach and several aims. The first aim is the one of detecting, let's say, a good energy configuration that models these, the interaction I was mentioning before. And also, let's say, to understand how regular let's say, the equilibria configuration can be. And so there have been several results in the direction of regularity for this type of problems that are due to Larsen and then Carrozza, Fonseca, and Passarelli di Napoli. Very recently, there have been there is the study by Babadajan, Urlan, and Rindler, where the authors want to model, let's say, the appearance of concentration phenomenon when one assumes that one component of the material, let's say, becomes smaller and smaller. I'll try to make maybe a little picture at some point to clarify. So essentially, the idea is that you are given a sample, a domain, let's say, Miga, let me, why now I don't see my, oh, I thought I could see my blackboard, now I don't see it. No, I don't see it, let's see, now I feel I could have tried before. I had the idea that I could write on my notes as I was doing, but now, is there any way of doing it? No.
Directly on your notes, if you want
yes,
to annotate
my notes, because I was trying. Now I feel guilty. Okay, so now I cannot do anything. I could have tried before because this was working this morning and now it doesn't. So essentially, okay, so nothing to do. I'm sorry. I cannot make any picture, so I have to just to speak. Well, or I can, let's see.
You can switch to the whiteboard, Elvira.
Yes, if I see now my whiteboard, I'm sorry, I feel so, because this morning it was going and now it doesn't. Let me see. Whiteboard, it's there. Let's see why it doesn't sit. I hope now. Yes, let's see. I feel here. So if now where is now the...
Another option is not to...
Yeah, no, I'm trying to know, because this morning I was able to
full screen.
I tried and I was able to write on directly on my notes, but now it doesn't work. Okay, anyhow, just to let you fix the idea. Now I guess you can see, you have, let's say, a sample omega, and then you have some inclusion by a different material, let's say, or the zones where your material has a different energy. And so let me call this colored zone will be my E. And so this is my E. Okay, and then omega is my open set. And the idea is that I want essentially to identify the energy that I'm going to show in a second using the characteristic function of this set T. So namely, my characteristic function chi E is, or simply chi, let's say, is going to be the function which is 1 whenever x is in E and is 0 when x is in omega minus E. And this will be essentially the characteristic function that I will be playing all the time. So let me see if now I guess you can see now my slides. So the idea is that I will use this, the presence of this field to start writing the energy. And the energy will be indeed the sum of these two contributions, one given in E and the other in omega minus E, and some other terms that won't be so crucial for the analysis, because some of them are linear terms or terms which are very easy to be handled. And then according to the modeling where there is a perimeter penalization, let's say, between the interface between E and omega minus C, I will take into account a perimeter term. So let's say the following. In the case of damage, the point is essentially in the damage for nonlinear elastic material is that when one passes from one point to another of a certain material, then it happens that when you evaluate the deformation gradient, and then there is a difference between the energy in W0 and the energy modeled by this W prime 1, and this difference overcomes this a fixed rate K, then the sample prefers, let's say, to pass to the lowest value. And this is essentially an evolution problem. This is something which happens as the time passes, but clearly it's important to understand what happens at every finite time in order then to go to an approach with time in terms, let's say, like a piecewise continuous step evolution, let's say. So it is important to take into account a minimum problem as this one, which is here, which is, let's say...
Sorry to interrupt. We are not seeing the slides.
You don't see, but oh, wow.
We are seeing the whiteboards.
You still see my board? Oh my God.
We are seeing the whiteboard.
It's that I feel...
Change the screens.
I strongly... Now you see it.
Yes,
you see it now?
Yes, perfect.
I'm sorry. Because I saw that there was, because I was not maybe sharing. Okay, so essentially the idea is to minimize this energy at each fixed time and understanding which are the minimum values, when there are minimum values, in the couple chi and couple V, and couple chi and V. The point is that usually, I mean, there are no enough properties on W, that allow to detect a minimum value. And so one needs to find another associated energy which shares the same properties in the sense that it admits the same infimum, and on the other hand, I mean, it really has a minimum, and so essentially this is what happens using relaxation techniques. Well, if then we want to model, let's say, not the damage, but the really what are called the optimal design problem, one has to look essentially first for the compliance. So essentially, given a configuration E, one wants first to minimize in the deformation U, and then the aim is to essentially maximize the opposite of the compliance, to have the best model that maximize, I mean, certain requirements as good properties. Actually, this is something that cannot be done through the direct methods because this is a max-min problem, but at least the direct methods allow to avoid, let's say, to understand which are the worst possible designs. And I want to say that the first modeling, this is what I was mentioning at the very beginning when I was quoting, for instance, Kohn-Strang, are models where there are no perimeter penalization among the interface, while the presence of this term is the one that I will consider always in my talk. And I hope to be clear in a moment why is it so useful. Well, as the first observation is indeed the following, is that if there is, if one wants to go for for instance, the damage model or the worst design, and one neglects the presence of a perimeter, then one wants to consider this minimum problem. This minimum problem does not have a solution. And the idea is that, okay, you need to look for a closer one. The point is that this sequence chi E is a sequence which, if I want to consider an infimizing sequence, is a sequence, let me call it chi E. This sequence takes value just in 0, 1, but of course, up to a subsequence being clearly bounded, it will have a minimum, which, a limit, I'm sorry, which takes values in the entire interval 0, 1. And of course, this is not what you want to understand what is your limit configuration, because a function that takes all the possible values between 0 and 1 does not describe then really a set like your initial one's EN. That's why the introduction of the perimeter term is useful. And in fact, this is what the model that I'm going to propose, following the idea by Ambrosio and Buttazzo. I want, there are a list of models that I've been considering in these years, and but I will mainly focus on the first two. The one where both the energy W0 and W1 have the same growth, and these results have been obtained in collaboration with Grassa-Cavita, and others where the energies W0 and W1 have really different growth. And these are recent results that I obtained together with Anna Cristina Barroso. Then other models that I'm not going to describe today are those related to plasticity and to fracture mechanics. This one with José Matias and Marco Morandotti, and this about fracture mechanics with Rodica Toade. Here I'm avoiding this analysis here because it involves also surface term, and I prefer now mostly to give ideas about, let's say, the true energetical behavior more close to the model I started describing before. So, well, this is going to be my functional that you have already seen many times, that I'm going to call f of chi and u, and I'm going to say something more precise about the field chi. chi will be indeed the field which lives in BV of omega with the values in 0, 1. And U is going to be, okay, this must be a W1Q, I'm sorry. This is going to be the field that accounts then for the deformation gradient. And having in mind the real optimal design problems, then it is useful also to include a volume constraint, let's say, that one wants to prescribe the maximum amount of material E that you want to put in your domain omega. Then you can consider some loads here, some volume forces, and then you can have, this is going to be always a linear term, so let's say it will combine well this P prime with the summability exponent of the field U. So I said that I wanted to say something more about the field chi. To do that, I prefer first to recall very briefly what I mean by BV function. And so, a BV function is an L1 function, or can be even vector valued, that has a distributional derivative, which is a bounded Rodin measure. And I will say that a set E is a set of finite perimeters. So let's say a set which takes value in omega, and that is defined in omega, takes value just 0, 1, whenever is distributional, the total variation of this distributional gradient is indeed finite, and I can describe in this way. And the perimeter that I'm going to include in my energy will be always understood in the sense of this total variation here. Well, okay, I have to say something more. If I consider just a generic field in BV, its distributional derivative is going to be modeled essentially in 3 parts. One part, which is, because this is a measure, so it can be decomposed with respect to any measure that we want, but the most interesting one related to the nature of the field U are the first one, which is the Lebesgue measure here, plus a jump term, where essentially this is a rank 1 matrix described through the difference between, let's say, the two side half Lebesgue limits, let's say, of the point U, times the normal to the set where essentially there is no there is this jump between these two values, and then a counterpart, which is somehow a measure in between the Lebesgue and the jump. When this is what happens for a general BV field, but when we have a perimeter term, our function chi, indeed, has no Lebesgue part, or essentially it is identical equal to 0, and no counterpart. So the only part that describes this distributional gradient is going to be essentially, if you like, the normal to the interface where we are in E or outside E, because, okay, the only possible values are 1 and 0. I have to say that I hope this won't create confusion. Usually there is a convention to say that when we have the field chi plus is usually always the set where it takes the value 1, and chi minus is where it takes the value 0. But because of some other interaction with the field U, this notation won't be the notation that I'm going to adopt won't be, let's say, so standard, and I hope then I will be clear when I will use it. So, okay, this is the energy again, as I was saying, and I want to say that in some case one can even prescribe a boundary datum on the field omega, but this also does create problem. And as you can see, I'm neglecting the bulk loads because I'm assuming they are very nice to be dealt with. Essentially, they are continuous for the topology I'm going to consider then. As I said, the energy, the initial energy cannot have a minimum. So once one wants to replace the energy F by its relaxation, and its relaxation is going to be described in this way. I hope not to be very sloppy about that, because my energy are always, let's say, assumed to be coercive. I can say that I can characterize these, at least at the beginning, can characterize this calligraphic F, which is the greatest lower semi-continuous functional below the given F, towards this sequential characterization when I require that the field Chi-n go to Chi in L1, and because of this term, they're going to go up to a subsequence weakly star in BV, and the fields UN go to U in L1 of omega. And again, because of the coercivity, they are going to go, let's say, either in BV, if I assume the density W1 and, okay, W0, this is a type, with growth P, or in BV whenever, I mean, again, weakly star in BV, if I assume that W1 and W0 will have growth 1. What's the point? The way it is defined, it is, let's say, well defined. The point is that we would like always to have a representation for this functional F whenever this is possible. And this was my first aim. So in the case where both the two densities, W1 and W0, have P growth from above and below, we were able, I and Grasa Carita, to characterize, to represent this functional calligraphic F. And this functional calligraphic F is given by an expression very similar to the original one. So the perimeter term is still there, and we do not have the original density, but we have the Murray quasi-convexification for each fixed entry chi of W1 and W0. Namely, I mean, the quasi-convexification with respect to the second variable, of this function V of A and Xi, which is here. And so far, essentially, there is no interaction between chi and u, and there is a nice representation. The other question is that, okay, it's a nice conjecture, how to prove it? And I mean, what is this QW I just said? If you want, I can go back, but I mean, it should be so far pretty standard. The point is that how to obtain this representation? Well, the idea was to prove, to get a double inequality. So first we proved that this term is, this energy here is always less than or equal the limit inf along any converging couple Chi-n UN towards Chi-n V. And then this has been actually achieved via decomposition lemma, so namely replacing this sequence UN by another sequence which has lower energy, but such that its gradient is P equintegrable. And then the opposite inequality has been obtained usually constructing an ad hoc recovery sequence and exploiting other results for energy density, which are energy density V, which are not homogeneous, because indeed in our recovery sequence we fix the field chi. Well, what about the case where W1 and W0 now have growth 1? And why this is somehow interesting? I mean, even to understand which are the difference with the case where there are different growth. The point is that once we want to understand how calligraphic F looks like, it's important to look at this calligraphic F from a different perspective. So it's not trivial, essentially, given any couple chi and V or chi and U, to get a lower bound and an upper bound in terms of a certain conjecture, but it's more natural to make the following observation. Namely, the starting function on f of chi and u, here it's, it's written independent, for the fixed sample omega. The point is that this expression, the right-hand side, has a meaning no matter which open subset of omega we consider. And as you can see, this is a measure. So the point is that it's natural to expect that even the relaxed function of calligraphic f is a measure again, or at least under natural assumption on V, one can prove that this calligraphic f is still a measure. And this is what we have done. And this led us to the following representation, namely that this field, this energy, relaxed energy, calligraphic f of chi and u, is the sum of three contributions. One contribution, which is the natural one in the bulk, very similar to what we obtain in the true Sobolev case, plus another contribution in the set where the counterpart of the total variation of u concentrates in omega, and a surface term. And here is where my understanding of plus and minus changed with respect to what is normal for chi plus and chi minus. So essentially, I'm considering the field chi u as a unique field, and this is the half Lebesgue limit, let's say, in the set where this vector of components chi and u jumps, has different values, and chi u minus is the other according to the given normal nu, which essentially does not mean that the components of the field chi u plus are always 1 and u, but they depend on the choice that we take for the normal, and so I'm using this notation for the sake of brevity. And let me quickly also mention, okay, there is a typo, this is a lim sup. This QV infinity is the recession function of the quasi-convexification of V with respect to the second variable. The complicated part, let's say the most complicated part, is to read this surface density. And this surface density takes into account essentially the interaction now between the field chi and the field u. Well, this interaction is modeled through this density chi, which is computed as a minimum problem in a cube oriented, through the field nu, and which involves the recession function of QV and the total variation of chi. What I wanted to say is that it sounds a bit, involved, but is quite natural where it's just chi jumping or just u jumping. Namely, this density, where u has no discontinuities, but just chi has, is nothing but the total variation we started with, on the set where chi has no jump, so essentially we are either in E or in omega minus E. This is the recession function of the quasi-convexification, while on the other part, we got essentially the full interaction between the two fields. The way we computed this energy was, as I was mentioning, considering the coupled chi-u as a unique vector, just taking into account that this new vector u as a distributional gradient whose absolutely continuous path with respect to the Lebesgue measure is 0 for the first component and the gradient of u in the second, and the same happens for the counterpart. Of course, this result, was, let's say, technically interesting because it was not already covered by the literature, namely because there was nothing that was already covering this model. So the most similar result that we found was this paper by Barroso, Buscitte, Butazzo, Fonseca, and by Buscitte, Fonseca, and Mascarenhas, but no one of those was really, totally appropriate for our case, mainly because we also have explicit dependence of of the field u and not just on the gradient of u. And so we had to work by hands. And again, to estimate the lower bound, we proved this by two inequalities. And for the lower bound, we could make so far a direct estimate, not very different from what concerned bucket counter, from what I was describing before for the Sobolev setting, while for the real interesting part was to deal with the jump. I mean, let's say the part where there is discontinuity, where we are essentially across the interface, chi. And there it was really useful understanding how functions with finite perimeters behave. And this has been very well established now 30 years ago by Ambrosio and Brides. And we were deeply using their description, the properties of those functions. Then it comes, let's say, the interesting part, which is the fact that to prove the upper bound inequality, it is really important to prove that this relaxed functional f is a measure, and is a measure which is absolutely continuous with respect to our ingredients, namely the Lebesgue measure, the total variation of u, and the total variation of chi. And to prove that, we use the Georgian Letta criterion that I will show in a second. And then, okay, and then a mix of techniques. But I want really now to underline the importance of understanding that the functional f is a measure. Essentially, the Georgian Letta criterion says the following, says that increasing set function, so a function whose defined in an open set, and our f of u chi can be seen like that as a function of subsets of omega, open subset of omega, is an increasing set function. And it is a measure essentially when it satisfies these three properties. It is additive on disjoint sets, and this is not too complicated to show. It is subadditive on nested sets like this. And then there is a measure mu defined on the Borel subset of omega, which essentially provides a control of now our functional f. And this measure mu, the candidate for this measure mu, as I said, is this Lebesgue measure plus d chi plus du. Well, okay, I guess I will skip the comparison with other damage model. And I want to say that this idea of proving that functional, the calligraphic f is a measure was technically involved, but possible, let's say, in the case where both the density W0 and W1 had the same growth. This is not what happened when we assume our energy density have different growth. Essentially, essentially there are two cases. One case is when one assumes W0 to have a certain growth and W1 to have another growth, or when we allow both of them, let's say, to have a control from below, which is different from the control from above. And the control from below can even, let's say, be weakened until b equal to 1, let's say, so p equal to 1. And of course, I mean, this is what happens when people has in mind mechanical application and, for instance, wants to model Monet-Rivlin material or Ogden material. So essentially, when this W0 and W1 depends from, let's say, the norm of the gradient and some minors of the deformation gradients. And of course, this looks from different controls from above and below. And this is, let's say, in our program, like the final target, but we are really, let's say, in some initial stage. And when I say we, I mean, I and Anna Cristina Barroso. Well, so let me say, which is indeed our model. Just to focus, just to start, the case where W1 has P growth and W0 is Q growth, still, let's say, for our purpose, fits, let's say, the energy where we have a different control from above and below, because our energy density will be indeed a convex combination through the field chi of the density W1 and the density W0. That's why essentially we are in the framework which was in the previous slide. The point is also that, okay, we are, for the reasons I was describing before, imposing again a constraint, the perimeter constraint among the interfaces. And the point is that, well, such an energy is for sure finite if we take the field U to be in W1Q, and here I'm assuming Q to be greater than P. But of course, because of the lower bound given by the presence of W1, the energy bounded sequences Chi-n, UN are such that the gradients of UN have a bound just in their LP norm. So it is, we have essentially a gap. That's why, I mean, a gap in a sense that I will clarify in the next slides. So even if we essentially write this functional calligraphic F in terms of the L1 convergence, both for U and chi, clearly the coercivity condition allow us to have a weak limit, W1P weak limit for U, and weakly star in BB for the chi. Of course, when omega is not that regular, it might be, I mean, there might be really a difference when taking into account W1Q and W1Q log. And of course, I mean, because of this convex combination, it makes sense to have UN just in W1Q log and not, so let's say, having more freedom than just sticking with W1Q. There is a wide literature on the subject of this gap problem in the case where there is no chi, and from the point of view of the relaxation, when the P here is strictly bigger than 1, the main contribution, I would say, is due to Fonseca and Mali, and their result has been extended recently by Sonegi in the case P equal to 1. But for our analysis, we are going to compare also with another result due to Acerbi, Buscita, Fonseca, where there is an extra assumption on the fields, on the density W1 and W0. But I will reach this point later. Well, okay, this is our goal. What is the difficulty? The difficulty is indeed the following, is that, as I was saying, if I start with an energy F chi-n gradient of UN, which is uniformly bounded, of course, I start with sequences UN which are in W1Q, but up to a subsequence, they just converge in W1P. So essentially, there is no problem in describing calligraphic F whenever the target U is in W1Q. But the complicated part is that what happens when U is in W1P and not in W1Q. And of course, there might be cases where this calligraphic F is still finite, but I mean, the field U is not in W1Q. And let me say why is somehow this problem so interesting, and why is known to be known as a gap problem. The point is that models of this type go back to Laurentiev. So let's say 1 century ago, I guess it was 1926, the year where this paper has been published. And the point is the following. Laurentiev was exhibiting an example of a lower semi-continuous functional in a certain metric space X, such that the infimum that this functional was taking on X was strictly smaller than the infimum that the field H the energy functional H was taken in a dense subset Y. And this was described through an example, but from our point of view, it's very interesting, let's say, the interpretation of this phenomenon due to Buttazzo and, I guess, okay, to Buttazzo and Meisel, which is the following. Essentially, we don't have a Laurentian phenomenon, so let's say an inequality of this type, whenever we can prove that the relaxed functional associated to H, when we take sequences that approach X in capital X, but they just live in a dense subset, in the dense subset Y, and when it happens that this relaxed functional coincides with H, of course, there is no Laurentian phenomenon. So it is really crucial to models to understand which are the functional H which have this property or which don't. And essentially, besides, I mean, the Laurentiev analysis has been done usually when Y is a set of smooth functions. In our case, having in mind the mechanical application, it makes sense essentially to consider different Sobolev exponent, essentially to reproduce the same type of analysis when X is a certain W1P and Y is a certain W1Q with Q strictly bigger. So the point is that, and this is in fact interesting, is that essentially there is also another issue in our model, which is the following. Namely, we cannot even easily say that our functional F is, the way it's written is always lower semi-continuous. So essentially there is still even open, let's say, the question of understanding the integral representation of F in the entire space using the entire sets of sequences in X, and then its relaxation starting with sequences which are in Y. So there are more problems about that. And the first results in this direction, just to also to emphasize the choice of the exponents P and Q that we have made, is related essentially to what has been described when the field chi is not present in the model. So the two main models are this one. The one that I was saying before, where we have both the P norm of the gradient and the determinant of the gradient, or just the determinant of the gradient. And there is a wide literature on this setting, essentially proving that if P and Q are not well chosen, let's say they are not, so let's say Q is equal to N and P is in between N minus 1 and N, it might still happen that the relaxed functional that I'm always denotes through the calligraphic G1 is not a measure. While also essentially in the case where P is identically equal to N minus 1 and Q is equal to N, there is an example due to Celada and Dalmaso which proves that this is not the relaxed functional of this density, of this energy G, using fields which are in W1N, but with convergence in Wn minus 1, is not a measure. So the analysis that I was showing before, where there is no gap, cannot be performed, and the description of this relaxed functional is not so trivial. So it is important, at least to avoid the Laurentiev phenomenon, to have good conditions on the exponents that ensure essentially the possibility of having this relaxed functional to be a measure. Well, this is what happened in the homogeneous setting, but it is also important, and I guess this example has a certain connection even with the model that I was studying, is when there is inhomogeneity. An example due to Gangbo shows that if I mean, the choice of the exponents P and Q made in such a way, let's say P is strictly bigger than n minus 1, Q is equal to n, and the energy is coercive, essentially doesn't, I mean, is not sharp when one allows also for inhomogeneity. Namely, if one considers the characteristic function of a compact set whose boundary as a Lebesgue measure which is not zero, then this functional is not lower semi-continuous. And the relaxed functional cannot be represented towards a regular measure. So essentially it is really, I mean, it's really interesting to understand which are the possible representations for these measures. And I want really to emphasize that the counterexample due to Gangbo is for a set who has essentially a boundary who has not finite perimeter because it's a Lebesgue measure is not zero. Then let me say, so which is our starting point, and the starting point that I was mentioning is this result by Fonseca-Mali that says that if we take P and Q, which satisfy this chain of inequality, then Fonseca-Mali were proving that indeed the relaxed functional of this functional GU is a finite Radon measure. So the point is that, okay, what happens? The question was that, what happens if we don't have, I mean, if we are not in this, condition? And it is interesting that besides this is a Radon measure, the point is that it might happen that this Radon measure is not the one that we expect. Even if, let's say, the energy is convex in this, or polyconvex as this one. So essentially, I recall you that a polyconvex function is a convex function of the minors, and polyconvexity is a sufficient condition where there is no gap between P and Q to represent the relaxed function. But in the presence of gap, this density G is no longer the natural one to represent the measured calligraphic G. So strange things can really happen when there is a gap in the exponents. Well, so let me go back to our model, and our model was the one that I started with, but now there is a gap. I'm assuming, for the reasons that I was specifying before, that essentially even without chi, there are a lot of complications if we don't impose this restriction for the exponent q, let's say q in between p and n minus 1 p. I recall you that capital N is the dimension where, or the domain omega lives. And then we wanted to find, let's say, conditions, at least sufficient condition that ensure that calligraphic F is a measure, or at least that it's something which is almost a measure in a sense that I will say. There are, we also have, but I guess I don't have time to enter to this in this detail, so I'm sorry, I skipped those slides. And the point is that there is these two notions that play a role. The first notion is the strong representation, namely the representation, the one that I was mentioning before. So saying that for any choice of chi and u, calligraphic F is a measure, or that F is can be just weakly represented. So essentially, it lies in between the measure mu and the measure of mu evaluated in the closure of A. So essentially, there might be concentration phenomenon on the boundary of these open sets. And we were able to prove, me and Anna Cristina, that indeed this also this functional F-lock, where there is also the function the functions chi epsilon moving, this functional F-lock admits a strong representation. The point is that what can we say in other cases, or if we can have an idea about, let's say, the densities of these F-lock with respect to the measures that are there, or at least with respect to the Lebesgue measure, or the measure and the measure decay, which are, let's say, the known measure that will play a role for sure in our limiting process. And okay, we could essentially say that there is a strong representation, even not for F-lock, but for F. And the other thing is that, okay, something about these densities. Okay, to do that, we cannot say nothing precise, because even of the counterexample, the Acerbi, Buscetta, Fonseca that I was showing you before, even if we assume our density V, the energy density we started with, already quasi-convex or polyconvex. But the easy idea that came to our mind was the one of the convex setting. So assume that V is already convex. So if V, capital V, is already convex, then we have at least a lower bound for our calligraphic F, and the lower bound in the energy is given by the functional F itself. And this is due essentially to the Joffe theorem, which is this one, which says that whenever we have a Borel integral of this type, depending on two fields, so let's say chi and gradient of u in this case, the functional associated is lower semi-continuous with respect to the involved topologies, the natural ones. So we get a lower bound for free, but still we can have a Laurentiev phenomenon. And let's also say something, that this assumption was not only, let's say, the only one that we made because the field F, it was very complicated to understand what is going on when we have polyconvexity, but also because this model, the convex model, matches a famous counterexample due to Zhikov, the one where we have essentially, this must be another U, but essentially where there is an energy density which looks like the norm of the gradient of U to the power P of X, with a Px which is nothing but the convex combination in terms of the set chi, of the set T, modeled through the characteristic function, between the two exponents. And this, in fact, essentially this model has been studied a lot in literature, and there are a lot of counterexamples showing that essentially when the field chi is fixed, there is no possibility of representing the relaxed functional in terms of a nice measure, which is just the Lebesgue measure. And so, I mean, the situation will be even more complicated if we allow chi to be a VV field. So essentially this exponent Px of the type I was showing before, so not at all continuous. But we were able to say that under convexity assumption, our functional F-lock, at least F-lock, admits a representation of this type. So essentially it is the bulk density we started with, the total variation of chi, and the singular measure. The point was that this singular measure in general, we are unable to say if it might concentrate in the set where chi concentrated. This is just singular with respect to the Lebesgue measure. So this was essentially not really satisfying for us. And so we tried to find, and this is a very recent result that we have obtained, under a stronger condition, essentially focusing on precise domains E. So precise characteristic functions chi of X. So we can fix the idea considering this model functional here, and we want to relax this functional in the usual way. And we could prove, even without imposing any restriction between P and Q, that whenever U is regular outside this nice set E, we do have the nice representation that we have for calligraphic F and F log. So essentially, if F is not just any set of finite perimeter, but has nicer properties, and I want to stress that, of course, it has nothing to do with the set of the, I mean, is really somehow, I mean, this assumption does not conflict with Gangbo contraexample, essentially. I mean, it's really emphasizing that this property here is crucial, but we also had something more. Essentially that the topological boundary of our set coincides with the perimeter in the De Giorgi set of our set. And just few words and then I'm done. This set T, I want to say, I mean, the regularity that we were imposing was the regularity detected in a recent paper by Thomas Schmidt, which says that E has to be a bounded open set, well contained in omega, and its topological boundary has to have the Hausdorff measure coinciding with the perimeter of V. And this property, which is, for instance, shared by every set omega with Lipschitz, open set with Lipschitz boundary, is in such a way, essentially, E can be approximated by the inside with smooth open sets, and let's say the difference between this open set, the given open set E and its approximants is always contained in the intersection between the flattened set of the boundary of E and the boundary of E epsilon. And also there is a good estimate, which is crucial for our purposes because in our model the perimeter is present. There is this inequality between the perimeter of the approximant and the perimeter of the given set E. And also there is an approximation measure for this set, which also of course then ensures that the characteristic function of key E epsilon goes strongly to the characteristic of E, strongly in L1, and of course the approximation on the perimeters. With these tools at hand, we were able to get the representation that I was mentioning. And okay, at least, I mean, we had this, I mean, a desired result, the first desired result, obtained by ENS, essentially proving a double inequality between lower bound and upper bound, and not a theoretical measure representation, which of course holds, provided that P and Q have the estimation, I mean, are in between, are in between n and then -1. And somehow we are bypassing Jacob counterexample because our field chi is not fixed during our relaxation process, and we can essentially avoid to have the concentration of measures in our limits. Okay, and then the point is that what happens when V is not convex, or even when its quasi-convexification is not convex. But this is another problem. So I stop here and I thank you very much for your attention.